Hello class, we continue angular momentum part 2. But before that, let's recall what we know. Okay. If we have an Hamiltonian, let's say over here is for case of harmonic oscillator acting on a ket n, and we get the energy n. If we are being more particular for the case of harmonic oscillator, then we have like the following: n plus half n. We're using bra and ket notation. Okay, over here your n takes from 0, 1, 2, blah blah blah, it's integer. Now for this case, your wave functions n is equivalent to ket n. Alright, you know how to do it. Okay, but however, for angular momentum, so in this case I put Li, so my I take x, y, z. Alright, this means that you have Lx commutations between these two, they are not equals to 0. Okay, Ly, Lz, Lz, Lx, and you can find other combinations. Alright, however, if they are together with themselves, their commutator relations just remain 0. That was easy. Okay, since these covers by right three-dimensional system, okay, because you have x, y, z component. Now we are going next to see how the eigenvalue equation. So the keywords is eigenvalue equation for angular momentum. They are of course an operator. Okay. Previously we learned that we have the L square operator. It's L square operator, which is denoted by Lx square plus Ly square plus Lz square. And if we check L square and Lz, they are equals to 0. Okay. Similarly, if you have L square Lx or also L square Ly, all right, they are all 0. So, but in this case, okay, we said L square and Lz operator share the same eigenstate. Okay, so what does this mean? It means that if you have an eigenstates of L and M, okay, so you have L square Lm will give you some eigenvalue, and you have Lz Lm also give you another eigenvalue. Okay, so this is the key. Okay, that's what happens when we are going to look at the next part. Okay, so the next part is actually what we call this under Lz. So let's say this is your eigenstate now. There L is called orbital angular momentum, where M is called the azimuthal or magnetic quantum number. Now look at this part. you can also rewrite this as Lm. So in such a way, your cat Lm is equivalent to writing a functions of ml. Okay? See, this one, and this, they are the same. Alright? Similarly, is given by these two equations. Alright? But what does this means? Okay? This means the L and M have some kind of relationship. Okay? Now look at your L square. The eigenvalue always correspond to L. If you have Lz, the eigenvalue always correspond to M. Okay? So if you choose L0, M0, so you get the eigenvalue of your L, H square 0, 0 plus 1, 0, 0, and similarly H0, L 0, 0. They just give you the same 0 eigenvalue. Okay, but L and M actually have some relationship. If L fix some values, M can take this part. So if your L is 0, M can be 0. If your L is 1, M is minus 1, 0, 1. If L is 2, M is minus 2, minus 1, 0, 1, 2. Or you can have plus minus 2, plus minus 1, 0. Or equivalently plus minus 1 and 0. Okay. In the unit of h bar, the angular momentum have the same length is given by that. Now look at this orbital angular momentum. So if it's 0, they give you the possible values of m and also the angular momentum. Alright. So where does this come from? If your L square, Lm, h bar square L, L plus 1, Lm, then your L is none other than taking square root h bar L, L plus 1. This is h bar square root L plus 1. Okay. Then once we have that, you can combine, you can compute, one can compute any eigenvalue that is correspond to L square and Lz. Alright. I will give more on matrix representation next, but you can try to have a look at the examples given by 10 and these examples. Okay, thank you.